Okay, let's do another Lagrangian method. So far we have been discussing problems related to mechanics where the systems were purely some masses connected and able to move in certain configurations. And in the introductory lecture I told you that the application of Lagrangian formulation is not limited to pure mechanical problems. It can be even extended to diverse fields such as electricity and electrodynamics. So this is one example which shows how the Lagrangian formulation or Lagrangian method of generalized coordinates and related concepts can be applied to a very entirely different problem, such as that of an LC oscillator. You are very familiar with the case of an LC oscillator. An LC oscillator is used to produce oscillations, electrical oscillations. Okay, so what we do usually, an LC oscillator is usually an integral part in the electronic circuits like Colpitt's oscillator or Hartley oscillator that you have done in your UG classes during practicals. Okay, and it produces some sort of electrical oscillations having a certain frequency, and the frequency is decided by the value of the inductance L and the capacitance C. And the standard value of the LC oscillation frequency, maybe you remember from your theory classes, electronic theory classes, that we obtained as something like 1 by 2 pi into some root of LC, right? 1 by 2 pi root of LC, that is the frequency of the LC oscillation. And to obtain such an LC oscillation, what we do is that we initially charge the capacitor. Okay, you have got a capacitor having capacitance C. You connect the capacitor to a battery of EM of V. So this is what we are doing. You have got the capacitor of C and you connect it initially to a battery, okay, of say EM of E or the terminal voltage V. So automatically that if you leave the capacitor for a long time, the plates of the capacitor will be getting charged until the PD across the plates of the capacitor is equal to V, right? So the capacitor is initially charged to a voltage V, and that capacitor, after disconnecting from the battery, is now connected parallel to or connected across an inductor having an inductance L, right? So what happens, the charges from the capacitor plates will be flowing through the inductor to the other plate of the capacitor. So you can see the electrons will be flowing from here. Electrons are flowing from here, and so it constitutes a current in the opposite direction. Okay, so this current I can be written as dq by dt, where q is the charge that is flowing. Okay, dq by dt. What happens is that initially the energy is stored in the capacitor, means between the plates of the capacitor in its electric field in the form of electrical energy, right? Okay, electrostatic energy I can call it. So it was different expressions you have learned. So it's equal to half CV square, one of the expressions. Okay, and once it discharges through the inductor, the energy stored in the electric field of the capacitor decreases, and it gets partially converted into magnetic energy, which is stored in the inductor. And in the case of the inductor, the energy stored is given by E is equal to half Li square. Half Li square. We are just making the platform for the discussion. Half Li square. So and finally, all the charges residing on the plates of the capacitor will be getting zero, and by the time the entire energy will be converted into magnetic energy in the magnetic field of the inductor. And the reverse process then happens. The plates of the capacitor will be getting oppositely charged. This becomes negative and the other becomes what? Positive. So you can see that during an LC oscillation, actually there is what is oscillating is the charge is oscillating. Some charge Q is oscillating between the capacitor and the inductor. Okay, or I can say that it is oscillating between the positive and negative plates of the capacitor in a sense, right? With the energy becoming magnetic energy and again converted into electrostatic energy and back and forth. So that sets in what is known as an electrical oscillation. Now this is a theory that you are very clear about. I just have reminded you about what we are going to discuss. Now our aim is to derive. Okay, I hope you remember how did we get this particular expression for the frequency. For getting the expression for the frequency, I hope that you just applied Kirchhoff's voltage law, and you just put, okay, the voltage across capacitor, C minus the voltage or plus the voltage across the inductor, put it equal to 0, and then you form a differential equation and you solve for the differential equation. You will be getting equation for an SHM, and from the equation for the SHM you solve for it, you will be getting the frequency of equal to 1 by 2 pi root of LC. That is a common method of solving the LC oscillator problem. Now let's see, okay, how to approach the same problem by using the Lagrangian method. Okay, so the first step in applying the Lagrangian method is to identify the degree of freedom of the generalized coordinate. So since it is not a mechanical system, I cannot talk about how many number of particles are there. Okay, instead I will directly think of which parameter can describe both the capacitor as well as the inductor. Okay, ഈ കപ്പാസിറ്ററിൻ്റെയും അതുപോലെ ഇൻഡക്ടറിൻ്റെയും പ്രോപ്പർട്ടീസ്, കപ്പാസിറ്ററിൻ്റെ പ്രോപ്പർട്ടിയും ഇൻഡക്ടറിൻ്റെ പ്രോപ്പർട്ടിയും രണ്ടും എക്സ്പ്ലെയിൻ ചെയ്യാൻ പറ്റുന്ന ഒരു സിംഗിൾ യൂണിഫോം ജനറലൈസ്ഡ് പാരാമീറ്റർ എന്തായിരിക്കും നമ്മൾ ചിന്തിക്കുകയാണ് ആദ്യം. Okay, so you know that what are the parameters associated? One is capacitance ഇവിടെയുണ്ട്, capacitance എന്ന് പറയുന്ന പാരാമീറ്റർ ഉണ്ട്, ഇൻഡക്റ്റൻസ് L എന്ന് പറഞ്ഞ പാരാമീറ്റർ ഉണ്ട്. നമുക്ക് കപ്പാസിറ്റൻസിനെയോ ഇൻഡക്റ്റൻസിനെയോ ജനറലൈസ്ഡ് കോർഡിനേറ്റ് ആയിട്ട് എടുക്കാൻ പറ്റുമോ? ഒരു ചിന്തിക്കുകയാണെങ്കിൽ മനസ്സിലാവും. കാരണം കപ്പാസിറ്റർ എന്ന് പറയുന്നത് കപ്പാസിറ്ററിൻ്റെ മാത്രം പ്രോപ്പർട്ടിയാണ്, ഇൻഡക്ടർ എന്ന് പറയുന്നത് ഇൻഡക്ടറിൻ്റെ മാത്രമായിട്ടുള്ള സവിശേഷമായ പ്രോപ്പർട്ടിയാണ്. അപ്പോൾ തീർച്ചയായിട്ടും എനിക്കൊരു പൊതുവായ ഒരു സിസ്റ്റത്തിന് വേണ്ടിയിട്ട് കപ്പാസിറ്റൻസിനെയോ അല്ലെങ്കിൽ ഇൻഡക്റ്റൻസിനെയോ ഒരു പ്രോപ്പർട്ടി ആയിട്ട് എടുക്കുന്ന ഒരു പക്ഷേ ജനറലൈസ്ഡ് പ്രോപ്പർട്ടി ആയിട്ട് എടുക്കുക എന്നുള്ളത് ഉചിതമാവില്ല. അതുകൊണ്ട് നമുക്ക് ഇവർക്ക് രണ്ടുപേർക്കും പൊതുവായിട്ടുള്ള ഒരു പ്രോപ്പർട്ടി അന്വേഷിക്കുകയാണെങ്കിൽ നമ്മുടെ അന്വേഷണത്തിൽ നോക്കാം. എനർജി ഇൻ ദ കപ്പാസിറ്റർ ഈസ് ഹാഫ് CV², whereas energy stored in the magnetic field of the inductor is half Li². ഇവിടെ വോൾട്ടേജ് ഇവിടെ വരുന്നുണ്ട്, ഇവിടെ കറണ്ട് വരുന്നുണ്ട് അല്ലേ. ഇനി നമുക്ക് നോക്കാം, കറണ്ട് എന്നുള്ളത് നമ്മളിവിടെ കണ്ടു. കറണ്ട് ക്യാൻ ബി എക്സ്പ്രസ് as dq/dt, റൈറ്റ്? കറണ്ട് ക്യാൻ ബി dq/dt, which I can write as something like q dot. Can't I write this one as q dot? dq/dt is the first derivative with respect to time, so I can write as q dot. ഇനി നിങ്ങൾ കണ്ടിട്ടുണ്ട് ഹാഫ് CV² എന്നുള്ളതിനെ നമുക്ക് വേണമെങ്കിൽ മാറ്റി എഴുതാം. Can you write in terms of the charge? Okay, so I can write this one as q²/2c. നമ്മൾ 3 എക്സ്പ്രഷൻസ് പഠിച്ച് ഓർമ്മയുണ്ടാവും. E equal to q²/2c. അപ്പോൾ ഇവിടെ കാണുന്നില്ലേ? So you can see that E can be written in terms of q here, and here E can be written in terms of what? Half L I. I is what? Q dot. So I can write this one as L q dot square. Half L q dot square. So now we can see that in both the capacitance property, energy of the capacitor is q²/2c, and the energy stored in the inductor is what? Something like q dot square. But രണ്ടിലും q എന്ന് പറയുന്ന ഒരു ക്വാണ്ടിറ്റി is not either as first derivative or as the quantity itself. You can see that q is getting repeated. അപ്പം ഈ കപ്പാസിറ്ററിൻ്റെ എനർജിയെയും ഉള്ള എനർജിയെയും, നമുക്ക് എനർജി അപ്രോച്ച് ആണല്ലോ അനലിറ്റിക്കൽ മെക്കാനിക്സിൽ. അപ്പോൾ ഈ രണ്ടുപേരുടെയും എനർജിയെ സൂചിപ്പിക്കാൻ വേണ്ടി അല്ലെങ്കിൽ എക്സ്പ്രസ് ചെയ്യാൻ വേണ്ടി നമുക്ക് ഉപയോഗിക്കാൻ പറ്റുന്ന ഒരു കോമൺ ആയിട്ടുള്ള ഒരു പാരാമീറ്റർ എന്ന് പറയുന്നത് ഇതിലെ ചാർജ് ആണെന്ന് നമുക്ക് തിരിച്ചറിയാൻ പറ്റും. Okay, so with this investigation, with this realization, we prefer to select the generalized coordinate as the charge that is flowing through the circuit at any instant. So let the generalized coordinate, so that is from discussion we understand that one, we come to that consensus. Let the generalized coordinate, okay, so only one coordinate is enough, generalized coordinate. Okay, B means our q, small q, be the charge, that is in place of q I will be taking capital Q. Q is small q is the generalized coordinate and capital Q is the charge, so they are the same, and we single just coordinate is enough, so we will take the degree of freedom is equal to 1. That's why we just select 1. Okay, now as we have seen, energy in the inductance, we have to form the Lagrangian, that's the thing. Energy in inductance, energy stored in the magnetic field of the inductor, energy in inductor, energy stored in inductor, I can say E, for the time I am just calling it as E, that is equal to, it is half Li², which I have written as what? Half Li². I have done some background work. that's equal to, in terms of that one, half L Q dot square. I'm writing it as half L Q dot square. Now similarly, energy stored in capacitor, energy stored in the capacitor, I can again just write, I'm writing as E itself for the time being, energy E equal to, so that is what, half CV square, or directly I can write as it is equal to what, Q square divided by 2C, because I prefer to write it in terms of the generalized coordinate. Okay, now just have a look at first equation. Let me say that this is 1 and this is 2. Okay, you know our aim is to get the Lagrangian. Okay, and the Lagrangian, see the Lagrangian of the system, L is defined as T minus V, which is the difference between the kinetic energy and the potential energy. But unfortunately, we have got two energies, 1 and 2, given by 1 and 2, and we don't call this one as the kinetic energy or the potential energy. Okay, so let's try to identify. Can you tell me which one of this energy can be regarded as the kinetic part of the energy or kinetic counterpart of the energy, and which one will be acting as the potential energy? ഇതിൽ ഏത് എനർജിയാണ്, ഇൻഡക്ടറിലുള്ള എനർജിയാണോ കപ്പാസിറ്ററിലുള്ള എനർജിയാണോ നമുക്ക് കൈനറ്റിക് എനർജി ആയിട്ട് കരുതാൻ പറ്റുക എന്നുള്ളതാണ് ചോദ്യം. ഓക്കെ, നിങ്ങൾ അതിനെ കൈനറ്റിക് എനർജി ആയിട്ടുള്ള, നിങ്ങൾക്കറിയാം കൈനറ്റിക് എനർജിയുടെ ഒരു ജനറലൈസ്ഡ് കൈനറ്റിക് എനർജി എന്ന് പറയുന്നത് എന്തായിരിക്കും, ഹാഫ് ഇൻറ്റു സം മാസ് ലൈക്ക് പാരാമീറ്റർ ഇൻറ്റു വെലോസിറ്റി സ്ക്വയർ. വെലോസിറ്റി എന്ന് പറഞ്ഞാൽ ജനറലൈസ്ഡ് വെലോസിറ്റി സ്ക്വയർ. അപ്പോൾ ആ രീതിയിൽ നോക്കുമ്പോൾ നിങ്ങൾക്ക് ഇവിടെ കാണാൻ പറ്റുന്നുണ്ട് ഇൻഡക്ടറിലുള്ള എനർജി അത് ഹാഫ് എൽ ക്യൂ ഡോട്ട് സ്ക്വയർ ആണ്, ബിക്കോസ് ക്യൂ ഈസ് ദ ജനറലൈസ്ഡ് കോർഡിനേറ്റ്, ദെയർഫോർ ക്യൂ ഡോട്ട് ജനറലൈസ്ഡ് വെലോസിറ്റി വിൽ ബി ഈക്വൽ ടു ക്യൂ ഡോട്ട് നമ്മൾ കണ്ടു. ആൻഡ് ഓൾസോ വി നോ ദാറ്റ് ദ കൈനറ്റിക് എനർജി ടി ഈസ് എ ഫംഗ്ഷൻ ഓഫ് വാട്ട്, Q dot. T should be a function of generalized coordinate, sorry, generalized velocity. So I can say that this is what, half L Q dot square. Appo potential, sorry, the energy stored in the inductor is regarded as what, the kinetic energy part. And the same manner, since energy stored in the capacitor is a function of the coordinate, okay, I will or we will just identify the potential energy as the energy stored in the capacitor. Okay, so and that is also justified some other way also. മറ്റൊരു രീതിയിൽ നമുക്ക് അതിനെ ജസ്റ്റിഫൈ ചെയ്യാൻ പറ്റും. നിങ്ങൾക്കറിയാം the energy stored in the capacitor in its electrostatic field, അല്ലേ? സോ അവിടെ ചാർജുകൾ റിസൈഡ് ചെയ്യുമ്പോഴാണ് ഇറ്റ്സ് ആക്ച്വലി എ ഫോം ഓഫ് പൊട്ടൻഷ്യൽ എനർജി, റൈറ്റ്? But in the case of an inductor, you know, the energy is due to the flow of charges. So means there is a motion of charges. So there is a current. As long as there is a current, there will be a magnetic field. And when the current ceases in an inductor, means when the flow ceases, when the movement ceases in an inductor, the energy is what? Zero. Okay, so in that justification also I can call, I can consider the energy in the inductor as some sort of kinetic energy, the energy related to the movement or the motion of something, motion of the charge of course here, and the energy stored in the capacitor is due to the storing, okay, or due to the static situation, the storage of the charges on the plates of the capacitor. So I can regard it as clearly as what, a sort of potential energy. So with this conclusion, I am forming the Lagrangian of the LC oscillating system, that is T is half L Q dot square, okay, minus what, Q square divided by 2C. So that will be the Lagrangian of the system. So let me say that this is 2B, okay, sorry, 2A, whatever it is. So let me say that this is my equation number 3. So once you got the Lagrangian in the proper form, now the task is straightforward. Okay, there is nothing to worry about. So what is the Lagrange's equation of motion? The Lagrange's equation of motion is d by dt of, see that we make it a repetition, dou L by dou Q dot, where Q is the charge on the place of the minus dou L minus dou L by dou Q is equal to 0. So that is our the Lagrange's equation of motion. Now okay, our task is straightforward. You have to just substitute it. What will be dou L by dou Q dot? So I think I can just go to the, what will be dou L by dou Q dot? So dou L by dou Q dot. So let me do it that. Okay, what will be dou L by dou Q dot? Dou L by dou Q dot will be see dou by dou Q dot of, okay, of course, half, okay, you know, see the first thing, half L Q dot square, right? half L Q square only. The first term will be there because second term is only a function of Q. So first term, of course, it will be L Q dot, right? Directly I could have written it, but I am just writing half L Q dot square minus Q square by 2C. So this is what is going to happen, and the second term will give a null result. First term will be giving you simply L Q dot, right? L Q dot, right? And what will be dou L by dou Q? Anyway, I am doing it in steps. Dou L by dou Q will be equal to, of course, it was a dou by dou Q of, okay, first term is not depending on Q, so it will be minus Q square by 2C, minus Q square by 2C, so it will be equal to again 2Q, so 2 and 2 will be getting answer, so it will be equal to what? Minus Q by C. What will it be? Minus Q by C. So now we can substitute these two things, therefore equation number 3 becomes, what will be equation number 3 becoming? d by dt of dou L by dou Q dot, means LQ dot, d by dt of LQ dot minus dou L by dou Q, minus dou L by dou Q is minus Q by C. Be careful about the signs and all. Okay, that should be equal to 0. And you can just rearrange. L is a constant, so L into Q double dot, taking that second derivative, plus Q by C is equal to what? 0, right? So what you can do, you can just divide by L throughout and rearrange. So it will be equal to, which gives you Q double dot plus 1 by LC, I am rearranging it, into Q, right? Into Q is equal to 0. And you know that this is something, okay, no, so this is of the form of a differential equation, like what, okay, which is of the form Q double dot plus some omega square Q is equal to 0, which is nothing but the standard equation, differential equation for SHM, okay, in terms of the variable Q. Therefore, on comparing, omega square is equal to 1 by LC, and it is now straightforward, 1 by LC, or omega is equal to 1 by root of LC, which is 1 by root of LC, or f is equal to 1 by omega equal to 2 pi f, so f equal to 1 by 2 pi into root of LC, which gives you the frequency of the LC oscillation. And you can see that the same expression that we are familiar with and we expected. Now, okay, hope that you got the idea. So this is one example, okay, of how you can just solve even problems which are not directly mechanical, but some similarity with the mechanics. Even those type of problems can be attempted by using the Lagrangian formulation. Okay, so that's one reason why we said that the Lagrangian formulation is a versatile type of technique that can be employed. Okay, now see, before we end up, as I told you, you can do more number of problems, different types of problems you can just get from any of the reference books. And I have seen that 2 of the reference books I have uploaded. The book by Upadhyaya is solving, okay, Upadhyaya. I have just uploaded one book, Upadhyaya, Classical Mechanics by C Upadhyaya. Classical Mechanics by C Upadhyaya. You might have used Mechanics by Upadhyaya, but see that the book of use for us will be Classical Mechanics by C Upadhyaya, and also another book, Classical Mechanics by we have Arul Das. Okay, these 2 Indian authors' books, they have got a large number of solved problems. Arul Das. Okay, see that you solve maximum number of problems on Lagrangian mechanics from okay, you can refer to Upadhyaya and Arul Das. These 2 are 2 nice books which describes so much of solved problems are there. You refer to the solved problem. First you try to do it yourself. If you are not able to do that one, please just refer to the solution and be thorough with the methodology. I think the recipe is very clear to you by the time we solved some 5 problems that is there. And I wind up this session by just assigning you one special problem, okay, which demands some knowledge of electrodynamics also. You try to attempt this thing as an assignment, keep assignment and all. So this is the assignment for you now. Find the Lagrangian of a charged particle moving in an electromagnetic field. So it is just again a level up problem. It's not mentioned in your syllabus, but let's try to do this one. the Lagrangian of a charged particle moving in an electromagnetic field in terms of the scalar and vector potentials. Okay, hope you remember you learned about the scalar potential and vector potential. The scalar potential phi and the vector potential A in electrodynamics, while you discussed about simplifying Maxwell's equations and all, right? So you have to, maybe it will be a bit lengthy, but you can just refer to better. Okay, maybe you need to have some reference, some assistance you can get from either of the two books that I have explained, Upadhyaya or both Upadhyaya as well as this Arulda's book. Both are giving you the solution of this problem. Please refer to this problem, because even though the Lagrangian of the system is not mentioned in our syllabus, we need to find out the Hamiltonian of the system later in the next module. Okay, and you can get the Hamiltonian of a system only if you know the Lagrangian of the system. So it's good that you do that. Okay, so I'm giving you the answer for this one is the Lagrangian of the system will be equal to T. T is the kinetic energy minus Q into phi plus something like Q by C into A dot V, where phi is the scalar potential of the field and vector A is the vector potential of the field, V is the velocity with which the charged particle is moving, and Q is the charge of the particle, T is the kinetic energy of the. So it is of the form T minus V. So you can see this is T, and so this particular entire thing will be nothing but the potential energy term. Okay, so you have to maybe make use of the concepts like see the Lorentz magnetic force, you know, Q into E plus V cross B. Okay, so Lorentz magnetic force F Lorentz is equal to Q into E plus V cross B, and then for that magnetic field B you can write in terms of the vector potentials, and you can just do that. Okay, so see that you try to attempt this problem as a assignment. Okay, if you feel with any difficulty, I can spend some time on that one later, but you just let me know about your difficulties if any. Okay, so try to do also a problem on harmonic oscillator, spring mass system. Okay, spring mass system Lagrangian. Okay, that also you can do as an assignment. And already I think I have mentioned to you about another assignment like see conical pendulum. These are some familiar common system, conical pendulum. Okay, so try to do as many examples as possible. Okay, also refer to the problems asked from this section in previous year net and gate examination, net plus gate examination. So use these days. Okay, so next week maybe you will get some free time, you can just work out more problems on that.